Okay, so I think we can start with session number 9 of the Probabilistic Machine Learning Reading Group. This time we have David Rios Insua, which is a researcher at the Mathematical Science Institute in Madrid. And he'll be introducing today, he'll give you an intro on generative models, a guide into the literature. So please, David.
Thank you. You can hear and watch the slides?
Yep.
Okay. Um, so we are kind of changing gears in with this session for the I believe it's the next 4 sessions. Basically, we've been going through various computational methods to handle posteriors in complex models. We went through Hamiltonian Monte Carlo, we went to variational inference, and so on. We also saw some of these tools in action with what are called discriminative models for classification and regression, mainly through neural networks. And today we are moving on to generative models. The plan is to provide a bunch of basic concepts and ideas that will be used in the next 3 days or 4 days. Then I shall explore a bit on what are variational autoencoders, then a little bit about autoregressive models, and then some final comments. That's the plan for today. Okay, so in machine learning, there's several subfield divisions. And the one that we cover today is generative versus discriminative models, which is, one of these names that the machine learning community have sort of invented. In traditional statistics, we had similar names for other things, but let's stick to the machine learning terminology. So the idea in generative model is that we are going to build or we need to build some kind of probability distribution for the whole for all the variables that we are interested in. I wrote that they're X, but it could be Y and X. The basic idea is that we are not going to do P, Y given X. That's not the object of interest, but that's the whole. We want to get some kind of model for the whole density, right? To add a little bit to the confusion, sometimes people, or we actually we shall be talking about conditional generative modeling when there's some inputs C, and we shall try what we shall try to build is the distribution of X given Z. For example, that could be C could be like some kind of input providing context. Could be like, for example, like a prompt in when you are using a large language model. And the difference with a discriminative model would be that in a discriminative model, you expect only one Y to be correct, whereas in generative models, when you talk about conditional generative model, you allow for several correct Ys. That would be like a sort of a bit simplistic, but that would be the sort of difference. There are several types of generative models. We shall be talking today and the next 3 days about what are called deep generative models. Basically, these are generative models which use a neural network to learn a map from the latent variable set to the data X. So neural networks or deep neural networks are sort of the key tool to learn the distribution which is of interest. There's other families. There's probabilistic graphical models. We saw a bit of them on session one. And basically, they map interconnected latents, n interconnected latents, to the observed d variables of interest. But then, I mean, the separation is a bit, um, let's say, artificial because there's deep probabilistic models, and I mean, there's mixtures of everything. And a little bit also, I mean, this is one of the things that maybe you can say, I didn't know that I had been doing generative models for, let's say, 30 years. I mean, the Stats 101 models that we study are basically generative models, mixture models, kernel density estimators, etc. So all these are actually generative models as well. One thing which is probably one way to differentiate is the kind of problems that one is interested in. And I put there several of them. The first one is generating new data. And that's the sort of, I mean, currently that's the more, let's say, cool or in application through what is called sometimes generative artificial intelligence. And actually, we had I mean, for a summary of generative artificial intelligence, more specifically on transformers and LLMs and a number of issues related with them. There's a bunch of material similar to what we are doing in a sort of shorter version at this site. And things that we can do from this is sample new images. One example, another application is for generating synthetic data. And Danny, for example, is doing, I mean, generates synthetic data from medical problems, from actually a probabilistic graphical model to avoid confidentiality issues. I mean, to make public data to avoid confidentiality issues. And in relation to conditional generation, with respect to generating data, there's examples like C could be a text prompt, and X could be an image. So you would have a text-to-image application, but there's other applications which are reflected there. For example, in image to text, you want to create captions, automate captions. In image to image, you want to provide color to an image. In a speech to text, there would be applications in automated speech recognition and so forth and so forth. A second major application is a classical problem. I mean, the previous would be a classical because you're, I mean, in stochastic emulation, that would be generating data. In density estimation, you want to estimate you want to evaluate P of X, right? And that's useful in a number of applications. Some of them we already mentioned. For example, when Carlos mentioned talk about distribution shift, so density estimation or evaluating the density at various points. It's a sort of mechanism or a tool, or provides the basis of tools for outlier detection, novelty detection. You use it in mixture modeling and so on. There's other important applications, multiple imputation, like based on the data X, you want to build a model of the missing data given the observed data, and you use this um, to impute the data that is missing. Is structure discovery. You want to, given the data X that you have observed, you want to provide some information of what are the most relevant latents. And that's useful, for example, when you try to, one sort of close project, when you generate a new molecules, for example, in drug discovery, and you want to try to find out what are the most relevant, let's say, or you want to explain what are the most relevant latent variables, pieces of molecules in those molecules that you are generating. Model-based reinforcement learning, in many applications. So data is not that abundant, and you use a model to generate the data, to simulate the reactions of the system that you want to control. Data compression is also important. Like the sets could be a smaller dimension of the X, and that would be a way to compress data. And of course, we must remember always that at the end, we do use all this to support decisions or to automate decisions, and that should be the ultimate goal of all this, I would say. And many of these actually are in the realm of unsupervised learning. So maybe that's a shorter way to explain what is generative modeling. So there's a bunch a large bunch of models, quite important models. There are in this screen. There's the models that appear in Murphy's book, and we're gonna do today the ones in red. So I'm gonna do variational autoencoders and autoregressive models, but there will be a session on normalizing flows, another one on energy models, and another one on diffusion models. The book also includes generative adversarial networks, but Pablo and Danny decided that we shouldn't cover this, right? So besides these chapters 20 to 22 that I'm covering, I'm giving a sort of um, quick summary of this, which, by the way, are also quick summaries in some cases, of some of the techniques. I shall mention other relevant references along the way. Any comments or questions or? Okay, so there's features when we talk about generative models. There's features to distinguish them. For example, the availability of the density, whether this is explicit or only implicitly, as in, for example, GANs. Whether we only, sometimes we can only get a lower bound on density, and typically because we try to maximize elbow, as we explain in sessions 2 and 5. And sometimes we only have an approximation. And another distinguishing factor, which would determine what technique to use is whether sampling is fast or if you need a fast sampler, you could use, for example, a variational autoencoder. But if you need it for other purposes and you're not that worried about sampling, you could use, for example, an autoregressive model, a deep autoregressive model. Training some of the models that we shall mention, we can do only maximum likelihood estimation and local maximum likelihood estimation, but in others, we'll use variational inference. Sometimes we'll in GANs, for example, we use or we tend to use a different technique based on game theory. Models also depend on or differ whether they have latents or latents or not, and whether these latents are compressed. And some of the models will impose some restrictions on the architecture adopted. For example, in normalizing flows, you need invertible neural nets, as we shall see in a few days. Once you have fitted or once you have learned the model, you need to evaluate such model as usual, and you look for metrics capturing various features. The first one is, of course, the sample quality, whether the samples that you are generating with the model would come from the sort of distribution that you are looking for, that you started with, or from the distribution of the data you started with. The second one refers to sample diversity, and that was discussed by Pablo on the second session when he was referring to variational inference, whether it is focusing on one mode or several modes, etc. That was discussed there. And it's whether we are capturing with the samples that we are producing, whether we are capturing all modes or just one mode or a few of the modes. And also the sort of typical, that's a sort of generic feature or evaluation feature of machine learning models, whether the model properly generalizes beyond training data. For this, I mean, there's actually no measure or no metric or I mean no way to cover simultaneously all these features in general. So there's and as a consequence, there's a sort of industry around evaluating generative models. One typical way would be to use a Kullback library divergence between the model Q and the actual P. I mean, between the model that we have that we use to generate and the actual P. And well, we again on session 2 and session 5, if I remember correctly, we talk quite a bit about this. In many of these, I mean, in the realm of GMs, P of X is approached or can be approached by the empirical distribution, and as a consequence, the cross entropy, which is the second term, the second term in this equation, can be actually approximated by the negative log likelihood on the data set, which is expressed by this expression in this expression. There's many others. There's two sample tests, and where the null would be whether both samples come. I mean, the sample. I mean, the observed data and the data generated by the GM, whether they come from the same distribution. That would be the null hypothesis. And there's many classical tests for this. I don't know, Kolmogorov, Smirnov, and so on, which have been adapted to high dimensions, right? And there's others, but I would like to mention, last but not least, human evaluation has been used. And a typical example would be these kind of models are generated are used to generate images, and a human or several human beings are I mean get paid to decide or to mention to evaluate whether these images are of sufficient good quality, or I mean are approach what um, they were, I mean, the purpose for which those images were generated for. Okay, so these are some basic references for this. The chapter 20 is in Murphy's is in introduction. There's a book length Tomchak, and there's this little paper which gets the basics of generative models as well there. Okay, so that was the introduction to the introduction. And we're going to move now on to various, on 5 classes. And today we're going to go 5 classes of generative models. And we're going to do today 2 of them. And both of them are quite important. The first one is variational autoencoders. They are quite important, but they are, let's say, better known than the other 3. The other 3 are important but not so well known, so that's why we spend more time on them in the next days. So variational autoencoders, what I'm going to do is define them. Then I'll put them in context with autoencoders, which are a family of neural network models, and it's let's say the deterministic version of variational autoencoders. I'll give some of the basics, and then I'll mention some variants. So variational autoencoders are generative models with latent variables. Said, right? We put a prior over set over those latent variables, and we'll see typical choices afterwards. And then there is a decoder. I mean, we convert sets into X's, or we generate sets, or we generate X's from the sets through a neural network decoder. So we move from sets to X. And then to make generative, the idea, remember we say that there was no like we introduce a randomness through an exponential family. So the whole thing is they're reflected, our latents with the prior, and then from set to X, we generate from some exponential family, which is whose moments, let's say, whose parameters are associated with the latent and with a neural network in such a way. So exponential families, typical choices are Gaussians for continuous and for discrete product of Bernoullis. This type of model, sorry, these type of models are called deep latent variable models as well. And when the prior is Gaussian, they are called deep latent Gaussian models. And as we explained in session 2, or as in session 2 and sessions 2 and 5, actually we have explained this in as well in the Bayesian neural network session, etc. So we have explained this several times. Computing the things of interest, computing this posterior and computing this marginal is computationally intractable, and hence we use variational inference. through a variational family, which in this context is usually called a recognition or inference network. And we use it as we describe in sessions 2 and 5 in detail to perform approximate posterior inference. So that's the basic definition. So let me insist. We have latents. We have a prior over them. We generate the excess from the latent. We want to generate the latent, the excess from the latent, and we code this through a neural network, and then we add the randomness to the exponential family. Okay, so this relates with an earlier class of models, which are autoencoders. And autoencoders are just a class of neural network models which originally were introduced to map inputs, the X's, right, into a lower dimensional space, the sets, right? And for this, they use an encoder, right? So the X's are encoded into the sets. And then the idea is that we use these sets to try to recover the X's, right? So we use a decoder from the sets to the X, right? And the basic idea is that we want these outputs, which is the transformation. I mean, is the first we encode and then we decode. So we want these outputs to be close to the inputs, right? And that's the standard. We're minimizing the square norm. That's maximum likelihood with normal noise, etc., etc. That we have described before. And basically, this can be seen as a sort of nonlinear principal component analysis, if you will. Actually, if this coder and the coder would be linear, we would actually be getting we would be recovering basically we would be recovering PCA. So VAs, variational autoencoders, are probabilistic versions of this, right? We've seen it. We've seen probabilities at least, and we'll see it in a minute. And there's two main differences. First one, as we saw, the objective function is log likelihood, right? There's no Kullback-Leibler terms as we have I mean, for example, in the elbow, we have a Kullback-Leibler term besides a likelihood term, right? And also encoding is deterministic, right? So there's a deterministic um, there's a deterministic encoding here, whereas in the VAE it's probabilistic, and as a consequence, in an autoencoder, we basically focus on getting the expected value, right? Whereas in the variational autoencoder, we care as well about the variance to get some kind of uncertainties and so on. We don't do a very good job, as we said in sessions 2 and 5. But we try to do it. So I gave the general definition, and this is a sort of typical example, a typical or a basic, simple variational autoencoder, which has this architecture or these features. So I mean, that's a joint of the X's and the Z's, right? In the usual way. We put a Gaussian prior, and well, that's the definition. For example, as an example, for binary observations, a typical model is we assume that the X, I mean, each of the coordinates, each of the X's from 1 to D come from a Bernoulli. They are independent, and the parameter it's a perturbation over the value of a neural network over the latence, right? And as we say, the in parallel to this decoder, we need a recognition model, and typically the recognition model is it's um, a distribution which tries to fit the target distribution, right? The target posterior. So we use this to approximate the target posterior. And a typical example is a normal based on I mean, its variable are the latent variables, and its moments are how do you say a mean, right, and a standard deviation, and the standard I mean, this is a diagonal matrix with the same sigma in the diagonal, sorry, and the mean and the log standard deviation comes from a neural network, right? So that's a sort of typical assumption. And here is we cannot see. Yeah, here is the typical idea is that C is some kind of funnel, right? The prior over Z, that's the encoding, right? Sorry, this is the decoding, right? Based on a neural network, and then there is the recognition model. It's an encoding with I mean, which reduces the dimension. I mean, that would be the idea. That's I mean, actually, that's a kind of nice sort of how do we say? Yeah, that's a kind of representation of the type of thing that we try to get. I mean, what happens is we start with typically we end up with because of the uncertainty and because the recognizer um, um, uses how do you say, uses not only the likelihood but also a Kullback-Leibler term in the elbow. Typically, we get a more blurry image, right? So that's a sort of typical result. So for training, the sort of generic approach would be typically a stochastic variational inference algorithm from sessions 2 and 5. So we would have, I mean, we study this in detail, but so I go lightly. So we have the inference model and we have the generative model, each with the corresponding parameters, right? We initialize them and we apply stochastic gradient descent, um, for example. Um, we get a random mini batch of data from the data set, right? We put a little noise on them, and then we compute the elbow and its gradient, and then update theta and phi using SGD, right? That's the generic. A particular expression of this um, for a variational autoencoder with Bernoulli likelihood and prior and Gaussian posterior would have this. Basically, this is an expression. It uses the reparametrization trick that Pablo described, and then it uses a gradient descent to do the updates. So basically, this is a particular case of the algorithms that were described on in session 2. Okay, so there's several variants. I've put 4 of them, but there's tens of variants of variational autoencoder. The first one is called beta variational autoencoder, and basically it's a sort of reformulation of the elbow, right? The basic idea is to get this decomposition with this weight beta reflecting here. When beta is 0, we get the standard deterministic autoencoder, and which would give let's call it more precise reconstructions. If we make beta 1, then we recover the standard variational inference objective. And the idea is, I mean, typically the idea is to reduce this beta a little bit to get like less blurry, in the case of images, to get less blurry images. Another version or a variant in this direction, and again, depending on this parameter lambda, we recover depending on how we get lambda and alpha, we recover beta bi, or we can get the bi or the deterministic, etc. Is this variant, right? Which essentially adds x and z, and the idea is in this case would be try to get x as similar to z. I mean, that would be the term. I mean, the sort of let's call it, well, at least the only image that I put was basically from image, but you can get data. I mean, you can do bias for text, for data, etc., and you can get several modes of data, and so you can combine in some domains images and text. For example, a robot which is capturing images and is receiving is capturing as well language or speech, right? So he needs to combine both of them to get a better or a more, let's say, more complete description of the world. That's the kind of things that are, for example, being discussed in what are called large world models. And this is also a discussion. I mean, a typical discussion right now whether we have sufficient with large language models to get general intelligence, for example. And other variants, we just put basically one stochastic layer at each side. So there could be several stochastic layers, and this is called hierarchical by, and so forth. Right? There's tons of variants. So some references. Uh, um, I based the discussion basically on chapter 21 of Murphy's. But it's I mean the well, remove the Tom stack, the Kingma Welling paper, that's where everything started, and operational autoencoders. Interestingly, I think they were not full. I mean, they're full, or at least it was not the core from what I read. The core was not to introduce bias, but actually to use or illustrate variational inference in. I mean, it was actually a more of a variational inference uh, paper in some class of models, right? But they have then they convert the paper in a kind of monograph, not a very long monograph, and this is a beautiful reference. I mean, if you want to study, I would say rather than this one, this is really nice. This is really nice. Okay, and let's move to the last one, autoregressive models. And again, that's one of these things that I mean, we've been studying time series for many years. I mean, not me, no, or not we. A lot of people have been studying them, etc. So many sort of oldies or old models are get included in this kind of models. So I shall recall several basic definitions. Then I shall sort of describe in some detail neural networks for autoregressions. I mean, trying to combine the sort of the old style autoregressions with neural network-based autoregressions. Um, this will allow us to sort of make some emphasis on some of the things that Daniel mentioned when he talked about Bayesian neural networks, and then talk a little bit about transformers, right? So that would be the plan for the last minutes. So autoregressive models are just appear or emerge just by using a chain rule, the chain rule, right? So remember that we want to provide this kind of models. So we want to provide a generative model. We want to provide a P of X, right? Right? Or simulate, or use it to generate data or whatever. I mean, all the issues that we mentioned, or to assess what is P of X, right? And we just choose the chain rule to I don't know, to decompose it as P of X1, P of X2 given 1, given X1, etc., right? And as we said in the first part, to add confusion, we could condition on some prompt or some context or whatever, and we would do the same. This should be a small p. We would get the same decomposition given C, right? So that's one possibility. One problem is that the more we get into this, this is more. I mean, if it were like if it were Markov chains, for example, then this would be bigger and bigger and bigger. So it becomes like a beast, and if it's bigger, then it's more data intensive, etc. So this is actually, I mean, that's a sort of general definition, but it's not very super useful. So typical things, it's to sort of limit limit the memory, limit the memory. And one thing is use a first order Markov assumption. So that would be, and this is a classic model in the literature, like autoregressive model of order one or order Q, or right? There's other ways to sort of make uh, the observations depend on the past through latent variables, like for example through state space models and so on. For example, when Z is a deterministic function of all the previous observations, we recover a type of or an architecture of neural networks, which are the recurrent neural networks, which are not much in use right now, as far as I know. But they were very relevant to facilitate the study of or the use of neural networks in studying sequences, and they were earlier. They were precursors of first LSTMs and then transformers. And finally, another sort of oldie, when zeta t is a stochastic function of zeta t minus 1, so we have a state space model in this case, and in particular, one example would be in the discrete case would be a hidden Markov model. So an alternative is to use a neural network for autoregression, right? And here I'm explaining like a sort of some early work using neural networks for autoregressions. So I change, please allow me, I change the x's to y's here, and I didn't have time to retype everything. That's quite old. So, well, quite old, a bit old stuff, and I don't have the files anymore. Um, um, so the idea would be like make us a Markov, sorry, an autoregressive assumption of order Q. So the joint distribution of the n observations would be, I mean, we would have a distribution over the first Q, and then we get this assumption. We make YT depend on the Q before. So that's the same kind of distribution. Sorry, kind of the composition of this one, but we limit it to Q instance. So we make the Markov assumption there. And the idea would be rather than the idea would be to convert this and use this as I mean, use a neural network to model this. The idea would be if we call let's call it x, so the notation is not the most fortunate, I would say. If we call x to these q antecessors, we would be using we would be forecasting the next I mean the next YT as through a neural network model based on the previous of the previous observation of the previous Q observations. So this is autoregressive, but it's non-linear. Okay, so it would be like a standard shallow neural network. So this could be, I mean, this would be like a sigmoidal tonnage or transformation. And then it would be like a linear combination of sigmoidal. So that's a sort of shallow network, a neural network, which we use to uh, um, forecast the next observation. Okay, so that would be we introduce noise, right? That would be the sort of model. But to make it, to give it a little twist and to improve predictions, we can actually combine uh, um, a linear model, a standard linear model, with a nonlinear RQ. So we combine a linear autoregressive model with a nonlinear autoregressive model. And the idea is that I mean we would like to explain as much as possible the forecast through the linear term, and whatever I mean there could be features that we are not able or yeah features data features that we are not in the forecast that we are not able to predict properly with the linear part, and we add a nonlinear part, which in this case is it's a neural network, a shallow neural network. So we put priors on the parameters. We have appear here the weights, the linear weights, these sigmoidal weights, the inner weights, and various hyperparameters. And we are able to introduce a MCMC scheme, which is there expressed. The interesting part of this is that of this model is that given for fixed gammas, this is a linear model, so it's super fast to simulate. And we are able to compute with some effort these likelihoods, right? These integrated likelihoods. So it's a reasonably fast. It's a reasonably fast in. It's a reasonably fast algorithm, right? Okay. That was a sort of what is called a fixed architecture. But we can, I mean, we could claim in this case, we could say, well, maybe there's no linear term, or maybe there's no. I don't need I don't need I don't need a nonlinear term, or maybe I have one nonlinear term, or three or seven or whatever. So that's why we allow the architecture to evolve. So we have as like I mean, it's like the idea is that we have all this family of models. We have a model which is just linear. We have a model. We have nonlinear models. So a model with which is nonlinear with just with one hidden node, with two hidden nodes, etc. And mixed models, models with a linear part and a nonlinear part with one, two, etc., etc. And then we need to define jumps from this. The dimensions of these models change, and we need to define move or acceptable moves from various I mean those models. And this is a reversible jump algorithm, which was a type of reversible jump algorithm. There's a which was described, I believe, by Miguel on session 3 or session 4, if I remember correctly. I mean, one of the good things of this kind of approaches, which was described by Daniel on when he talked about Bayesian neural networks, is that you can get you can get you can get um, mm, you can get a distribution over the architecture. For example, you can get that This distribution, it reflects the number of nodes. In this case, it would be suggesting an architecture with three, between 2 and 4 hidden nodes, and that's useful. Improves predictions, and well, it has a number of advantages. The problem is that these quantities get impossible, or well, very difficult or very costly in larger regimes. And that's why we need to do other things like variational inference and so on in large models. But this idea, the same kind of idea, using a neural network for the nonlinear autoregressions has been used in, for example, what is called neural autoregressive density estimators, which is the same idea, but with deep neural networks and using variational inference. This has been used as well, this same kind of idea with causal convolution neural networks, and a different idea because it's, as far as I know, only through maximum likelihood estimation, has been with transformers, which is the sort of most popular autoregressive model. So that's why I will talk a little bit about them, but not so much because we have talked about them before. Basically, transformers have been used for encoding, decoding, and decoding purposes. And let me go to the picture. So basically, there's the encoders, several encoders and decoder layers. Each of the encoder layers has something which takes care of what is called, it computes the self-attention. So basically, each term, for each term, we find how much relation is of each term in a sentence, or each token on the earlier tokens, right? And it uses this kind of operations. So we have full details with code in session 2 that Roy gave like 2 years ago, right? And we have how this is used in, for example, GPTs in session 3 of like 2 years ago. It was given by Carlos. Some references. Murphy, chapter 22, but there's much more to say. I would say it's not the super best chapter of the book. Some references on autoregressions with neural nets, more traditional ones. The attention is all you need paper. This is an excellent survey, but it's rained a little bit since 23. The sessions that we did on LLMs, which are studied in full detail, and some interesting paper. It doesn't say much. From a Bayesian point of view, it doesn't say much stuff. There's not much stuff new, but it's it's kind of telling this community to adopt a Bayesian approach. So final comments, some problems. As I said, some of these models actually lack a PML approach. So Carlos mentioned the other day on attacks, distribution shifts, and so on. So for the case of LLMs and transformers, there's lagging work on this, and also attacks on unsupervised learning. And basically, remember that we have been talking quite a bit on unsupervised learning. Attacks are also lagging, so that's an important areas to work. And final comments, remember that we shall be doing normalizing flows, energy models, and diffusion models. And that's it. I don't know if somebody wants to make any question or comment. Uh,
I have one quick question. You have said that with LLMs, it is not, I mean, with transformer-based LLMs, it is not possible to, I mean, it is not possible, not, but it hasn't been done. People been fully Bayesian about them or training beyond maximum likelihood estimation. I guess part of it is the size of these architectures, and because of that, I've seen some works that were doing Bayesian stuff, but just within the, for example, the last layer or the first layer or things like
right.
that.
Yeah.
What's your view, or what do you think about these approaches that are not fully Bayesian, but maybe get the best out of both worlds, or are they
Yeah, I
justified?
think that they are better, but we should work better. I think we should work more or people should work more on in that direction. Yeah.
In which
Sorry?
in which direction? Like being
For
completely
example,
100% Bayesian
I
about it?
mean, not just the last layer, but you could do sequentially several layers. You should try to do 2 layers at least, or 3 layers. I mean, explore a little bit more the limits.
Hmm.
I mean, that might be an interesting problem. Uh, Also, the idea I put that this I put this problem to Daniel, but we were not able to. The ideas that I explained, the old ideas that I explained, were with sigmoid transformations. But I think you can speed them up with ReLUs and so on. So maybe that might be another problem to explore. But we were not able to be successful. Yeah.
I might
And
ask. Oh, sorry.
other points of view. I mean, uh, this position paper has some other ideas.
Hi. So thanks for the talk. Um, I'd like to ask also related to Pablo's question. So, what do you think that in contest learning has to say in this Bayesian perspective
Right.
on defending against attacks for LLMs?
Yeah, I read a bit, not a lot. So some people claim in context learning is Bayesian, but there's been some papers which say that it's not actually Bayesian. I can recover them and send them. Yeah.
Great.
But I guess that depends on the way you define it, right? I mean, like
Define
I'm
what?
thinking of these prior data fitted networks, for example, define a way of doing in context learning that leads to Bayesian inference, right? Amortized one.
Maybe. Um, yeah.
Was that what you were thinking about, Carlos, or?
Yeah, I mean, I think it's a great opportunity for us because it's a way of doing protection experiments without having to intervene on the weights. So I really think that it's a very 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 interesting path for us to follow and explore. And actually, as you say, I mean, there's a lot of room for interpretation of whether this is Bayesian or not. But the intersection of how to build priors and text, I think, yeah, I think it's also a powerful approach to defendants in this area.
So maybe we can share, or Pablo, you can share and add them to the references here or something.
Yeah, yeah, we'll send it when we send the email because I don't have it right now
Yeah,
here, but we'll
right.
send it.
And maybe if we have time at the end, if we have spots, maybe we can talk about this.
Sure.
Okay. Well, yeah, thank you for the discussion. If there are not any further questions, I think we can leave it here. Thank you so much, David, for the interesting talk, and I hope to see you in 2 weeks.
Okay, thank you.
Okay,
Thanks to
bye bye.
everybody.
Thank you.
Bye-bye. Bye.